Making another video, draft physics and such. So just as a response to clarify to Hofladay on a couple of the subjects, the Stern-Gerlach, quantum locking, maybe even some lensing. These are subjects I have touched upon in the past. I don't think they're nearly as important as explaining magnetism and gravity, but okay, let's deal with them. Even though I have limited access to the actual experiments in some cases, but anyway, let's play along. So off to the drawing board. I guess I should have gone the other way. Anyway, alright, so let's do Stern-Gerlach first. So the idea is to take silver atoms, you heat up some silver, you create a little bit of a obstacle course for it to go through to try to get little silver atoms moving in a straight line. Who knows if they're atoms or clumps of silver, who knows what actually is going through the experiment, but it's bigger than, they're atoms, not electrons, not protons, so it's a beam of atoms you're attempting to create. Who knows what their actual velocities are, whether they're consistent velocities or the same velocities. One can only conjecture regarding such things. Alright, and you're putting them through a device that is specifically designed for this purpose, apparently. It's not like an accident or something. For some reason they thought there was a necessity to do this experiment, so it wasn't like it just happened as some sort of accident. Oh, I should have done that part in red. My mistake. And I certainly should have done it more proportional. Alright, so the idea is to have the one pole of the magnet and the other pole of the magnet created in some bizarre configuration. So obviously this magnet would be connected to some other magnet that would have a north pole and a south pole. So you're just taking two magnets and essentially, they use electric magnets, but it's the same idea. You could sort of imagine that they're just configured two magnets so their poles are opposite, and now you send the silver atoms through this device. So the device is this kind of shape, it has a the device is consistent this way. There's the whole device is this way and this way. So you're shooting it through the length of the device, and the device is whatever, foot long, who knows how long it is. The path that you're shooting it through. So those are details. Can't really give them to you. Alright, so let's just redraw that as you're going through the field, and the uneven field, and so we'll just draw this part of the field like this or something, I don't know. Alright, you're just going to try to shoot the atoms through that, along that pointy edge. So you're going to try to shoot it right along this pointy edge and get it to go across, and when it goes across it creates presumably a pattern. So when there's no magnetism, there's a bar of light. That's which we're told to believe, we're expecting. So the bar would be like this shape compared to the input of the device. So as the beam's going through the device this way, this is what you get on the other end when it's not on. And then as you turn up the magnetism, you end up with apparently you can go through transitions, where the pattern will get like that, and then ultimately the end result will be two dots when the magnet's at its highest energy level, something like that. Alright, so what I would argue as explanation is that as the atoms are going through, they're basically using silver atoms. So why silver? The simple answer would be silver's a really good conductor. So it's going to do the Lenz law thing. It's going to do the paramagnetic. It's going to basically, as it gets close to the north field of a magnet, if it goes close to the north field, it ends up going north. That is, its atoms reflect whatever field's affecting it. And so if it goes south, if it gets too close to the south end of a magnet, then its field goes south. Then it creates a south field, and those two become repulsive. So it's the maglev train kind of thing, whatever, in the sense that whatever it moves towards, it ends up creating that opposite surface. So it becomes reflective to the surface it's exposed to. So it just automatically just becomes repulsive to whatever field is affecting it more. So the argument would be that where the little point is, it's a little tiny little field there, very directed amount of magnetism. So when it goes towards that at all, because that's a very strong field, so it's a very strong field hitting it, it very quickly reacts to the strong field, goes north, and so it starts repelling and it moves in the southern direction. Now the south field, in this case, we'll use what this is, north top, south bottom. So as it moves towards the south field, that field is much weaker because it's been cut out, it's been bowed, it's been reshaped to be weaker. So it takes it a lot longer before it starts to feel the effect, and it starts to turn reflective. So it turns reflective, say, much further down. And now it's going to push the atom back up again. And the atom's going to get pushed and pushed and pushed, and the push will start weakening. But obviously the atom has velocity, so that it can maintain. So its initial velocity will essentially be its consistent velocity. So it shoots up towards the little peak again, and the peak doesn't affect it until all at once kind of thing. It's a no field because it's such a small area that the field is affecting something that it isn't, you don't feel it until you're right there next to it. So again, it overreacts, goes north, rebounds again, too harsh, goes kind of deep into the southern field again, reacts. So instead of your silver atom going through the device in some way like a straightish line, if you had an even field, it'd be a straight line because the herky-jerky would be even. It wouldn't go up fast, down slow, up fast, down slow. It wouldn't have any unevenness in its velocities. So all the velocities would be even, so it would come out to be a very even path. But because of the uneven field it's going through, so it's doing this eccentric motion. So as it's going through the device, it's essentially releasing, just like we would in gravity. And so when it's coming out of the device, where the device ends, it could be either going in this direction or it could be going in this direction, depending on which way, how many herky-jerkies it went through. And so the odds are it's either traveling from the base upward or from the top downward. And there aren't any other real motions except those two. So the stronger the outcome will be, more and more decisively two dots. The more energy you put into the magnetic field, the more disproportionate the field becomes, and the more jerky this herky-jerky becomes. So that would be the explanation. So you don't need to invent spin. You already have the idea of paramagnetic and Lenz's law. So we just combine paramagnetic and Lenz's law, and that explains why the atoms would behave erratically in an uneven field, why they would move, do a lot of moving in an inconsistent field, because they would be constantly switching their polarity. Alright. So, locking, quantum locking. Alright, so this subject has to do with the levitating thing you see with superconductive materials. So you super cool a wafer of something, and then you put it on a magnetic field, something creating either positive or negative, it doesn't matter. I think it can even be alternating current. So you can have an alternating current going through a bunch of wire, creates a field above it, and then you can just place this little super cooled thing on top of that field, and you can push it or place it in different locations, and it'll hover at any one of those locations. technically. Now, I don't think it'll do all the way down. I think it pops back up. And there's obviously a limit to how high you can put it, where it won't work anymore. But in the range of an inch or so above the magnetic field you're creating, it'll just hover there. You know, so it can be this close, this close, this close, anywhere in this, and it'll just stay. Now, again, it's Lenz's law, the basic principle. It's just the fact that an opposite field is created. So the first thing you can understand is if I turn the whole experiment upside down, it doesn't work. It won't work sideways because of gravity. So we know that it's not it's not doing something, it's just combating gravity. That's all that's really happening. So you can't turn it upside down and the whole thing will float next to it. That won't happen. Okay, gravity's going to let it fall. And Lenz's law is going to make it fall. It's not going to work. It's only working because you're going against gravity. So the force you're creating equals the gravitational force. And the gravitational force is created by what? Movement. Okay, so we're talking again against, you know, it's just a Lenz's law phenomenon. The piece of, they usually have to use some material that is conductive, so Lenz's law will work. Something that can do the eddy current thing. All right, so it has to be that kind of, it has to be a silicon, has to be a metal, has to be something where this effect can take place. And so I don't even know if I can draw this, but I'll give it an effort. So the idea is when you cool something, so I'm not going to argue that there's any real current that actually flows in something, but you know, it doesn't really matter one way or the other. But the idea is that when you bring a paramagnetic, like if I had a hunk of copper here and I swung a magnet into it, the magnet will slow down because the magnet will cause this material to go the opposite of whatever way the magnet's pointing. So if the north end of the magnet's hitting it, it'll go north and it will oppose the field. So it's just this idea of opposing whatever field it's being hit by, which means it's just a mirror of that field. And the argument would be is that with this with these things that are called you know, quantum locking, as he called it, these materials are supercooled, which means all the resistance is done away with. So there's no delay in the reaction, is what you could argue. With a hot material or room temperature materials, there's a whole bunch of noise inside of this material, and so it doesn't turn reflective, you know, as a perfectly consistent reaction. It takes some time, essentially, you could argue, for this little eddy current to go around because of the resistance. The resistance essentially impedes the progress, and so it doesn't create its end exactly as quickly as it could by the distance. So there's a tiny separation in distance, so that at the speed of light it's almost like an instantaneous reflection. But if you have more and more resistance in the material, that reflection is delayed and slow, and it's not reacting as quickly as the movement coming towards it. So the movement's coming in at a speed, okay, now the movement's being caused, let me draw it this way just to illustrate the gravity part. So the disk moves towards the magnetic field so the supercooled disk is coming towards the magnetic field, and we'll just draw the magnetic field as lines. And the only movement is the movement essentially inside the material is the movement caused by gravity. When you're pushing it, that movement will be responded to, but I mean, it's not a consistent movement. The one that's happening all the time is the down, down, down by gravity. So gravity's pushing down, and if it's creating a force that's not delayed, then that force will equal whatever force it has. So it'll always be creating the same amount as the gravity coming down. So no matter where you put it, because there's no losses in the system, that is, there's no delay, that at any one position, it's going to create exactly the same field response, which will be exactly the opposite to gravity. And so no matter where you place it in this field, it's going to create exactly the same amount of Lenz's law reaction. So it's not in some way being degraded, which is the key to it collapsing. So it's almost like the magnet argument. There's just this subtle little thing about magnets, is if you can stop them from flipping over, you can have them in tension, in free space, so to speak. If there was some rule that said the magnet can't just flip, you could place magnets in free space and have them stick there, stay there, by having two forces hold them in a position. But because they can flip, it ruins the fun. And the argument here is that it's the same rules. It's just that because of the heat problem making it less than instant or near instant, to do this eddy current reaction, the reflective surface doesn't go reflective quickly enough, so it's not responding exactly to the movement. It's out of phase with the movement, so then it can't balance the movement because it's too far out of phase with the movement. And it's not also equal to the movement. So you can sort of understand if there's any resistance in the material, and resistance might even be called blockage, where you're losing some of the momentum of the voltage. So some of the voltage is being consumed or destroyed, some of the current hits well, here, I'll draw it. So if you sort of understand that some ways of describing resistance is to say there's impurities and there's other things in the material, and the current has to go through and it hits those impurities and essentially loses its momentum, reflects off them. And so those are losses in the energy. So those losses in energy, the losses in reciprocal movement, represent clearly a weakening of what you're going to get out of here as momentum out. So your momentum out, depending on the resistance, is because you're going to lose momentum to these other directions, in terms of heat losses. So the higher the resistance in the wire, the less of the momentum gets through. And so obviously through that process, if there was something that was actually happening to the atoms, you're going to be affecting less of the atoms because less of it's going to get through in that way. So the point is with this reflection you're looking for is the only way it can be proportional to the so there's a momentum in towards it, a force. The force is hitting the material. The material, based on how well the atoms communicate with each other, you could argue, how they spread that force is going to dictate how silver they become, how perfect the mirror. And if the mirror isn't nearly perfect to the force that's hitting it, obviously it can't make the thing levitate. The thing will fall further in. It can't make more force, right? It can't overcome any force. So the best it can do is equal the force. So if it loses none of its, if it absorbs all of the force and converts it all into mirror, you're going to understand that it would perfectly duplicate the force that's coming at it. And the thing that makes it kind of we're back to the anti-gravity arguments about inside the center of a spherical object, how there'd be no a hollow object, there'd be no gravity. So the same argument can be made. So here's your disk, and when it's further away from the surface, okay, more of the surface is being affected. So even though the force is weaker, okay, in the sense that it's further away, so there's less force hitting the surface because it's further away, it's being hit from more locations, so more force is involved at the further location. And obviously when it's close to the surface, then you have the opposite circumstance where now you don't have as much surface involved, right? All these locations aren't involved anymore, and all you have are these, but the lines are much stronger. So it's proportional. The further out you go, they probably shape the discs to take advantage of that. They might even have a shape to them like a bowl. But anyway, it doesn't really matter. But the point is that's why it's always the same. It always ends up, it essentially makes for an even field And so no matter where you place the thing, the distance will make up for the exposure. So there's more exposure to the magnetic field the further away you go, but the field is weaker. And then there's less exposure to the field the closer you get, but the field is very strong. And so that's all that's happening. It's just reacting to gravity, and it's just that it reacts to it without any losses. So the reflective reaction is exactly equal to the force that hit it, and so it mirrors the force that's hitting it, which means it just mirrors gravity. So it just creates an opposite force equal to gravity, because gravity is the force that's moving it towards it. And that's all that's happening, not complicated. You don't need any quantum crap to explain the phenomenon. It just has to do with eliminating the time delay that heat and the time delay and the losses. So it eliminates the energy losses and the time delay, the phase delay, that heat can create in a conductor. And when you get rid of those two things, the reflection is perfect and nearly instantaneous, which means it can levitate things at any position, because it creates a completely even field at any distance that's practical. I think that's probably enough. Alright, then the lensing argument. So Hockley briefly just threw in there some kind of, so the typical lensing thing is they have some clump of crap, and then they have some little magic bits. You know, over here there's a little clump of crap, and over here there's a little clump of crap. And so they're pretending that this is a big giant pile of gravity, these disconnected things that have very low density, but somehow this is like a big giant heavy massive object, even though it's not massive at all. It's made out of suns that usually don't have much dense material, and a ton of empty space. So if you calculated the actual mass of this thing, it would be a tiny object compared to these huge preposterous distances. And so he was basically making some point that if they do the spectral analysis of these two objects, they'll find out they have the same spectrum. Well, yeah, the argument would be, obviously, if you're going to try to explain why these two things are over here, the explanation, as I've stated, would probably be that there was a physical explosion, that there was a galaxy, let's say, all nice and swirly and happy, and something blew up. One of the black holes inside of it blew the hell up, and the galaxy was basically just blown into two pieces that drifted away at fundamentally the same rate, because the explosion happened in the middle, and galaxies are kind of proportional in their density. There's as much on the left side as there is on the right side. And you can see it in the arms even. You could even imagine that there was an explosion, that the arms would tend to just move off as themselves. They would still stay arms, and they would blow off. Like if a bomb went off inside of me, you know, my head might go that way. It won't blow my head into little tiny pieces. My head will stay together, and my arm might fly off that way, and the other arm would fly off that way. They'd stay together as a clump. So that seems to me the reasonable explanation is, it's really there. It's not a lensed image. The stuff is really there. And the reason why it's blue shifted, by the way, just as a by the way, the reason why it's a different color is because it is moving much faster, because it was in an explosion, and it's moving very fast because it was exploded into those positions. So it explains why these lensed objects, you know, are often, you know, a bright white color, or even blue, you know, when the rest of all this crap is red, and that would explain why there's the difference in the color spectrum in terms of the shift. Why do they have a different shift profile? Oh, probably because they are moving differently than the rest of that crap. So, you know, there can be reasonable explanations. And again, you know, the thing Hockley hasn't explained is all the places in space where there's absolutely no lensed images where there should be. They have images of the center of the galaxy where they think there's a big black hole, and they have stuff swirling around it. Not a single bit of lensing happening in this insanely powerful gravity. It's insanely so powerful, it's moving suns at insane angles, supposedly. Yet no lensing. It's not lensing the background at all. Not a single photon getting bent going through that galaxy. I mean, come on. So there's no consistency. The images are just a mess, and you know they're just, this is insanely weak evidence. He won't call it what it is. Confused, messy, dirty, sloppy, incomplete, indecisive evidence. He won't say those words. He'll just keep pretending this is proof, and we can declare it a fact based on this very, very, very barely reasonable speculation. And that's all we need. Barely reasonable speculation. That's the standard of proof. All you need is barely reasonable speculation. Convict. That's it. That's how. This is just a complete hypocrisy. And yet, if I speculate anything, I have to have more than one source, and I have to have more than one experiment that proves it, and I have to do this, I have to do that, and I have to do all the experiments. I mean, it's just a pile of crap. This is such a double standard. Again, go ahead, explain to me how the interferometer, the half-silvered beam splitter, the most famous beam splitter in the existence of beam splitters, is the half-silvered mirror. Well, why doesn't somebody explain to me how a half-silvered piece of glass could possibly be 50-50 and split the beam 50-50 when the glass is going to already split more than a quarter of the light? How can the mirror be 50-50 if a quarter of the light's already been split? It would have to be a 75-25 mirror, wouldn't it? I mean, they have simple flaws, catastrophically irrational flaws in their logic, and he lets it all slide. This is the goddamn, sorry, I mean, the hypocrisy is so disgusting. These people are so duplicitously unfair in their evaluation of evidence. The authorities can say anything, it doesn't matter how loopy and crazy, and every dissident is a tinfoil hat, talking out of his ass, bullshitter, you know, unless they come up with the videotape. Unless I show him, okay, the positive and negative force or something in a videotape, he'll never accept it. Until one of his guys says it's right. I mean, it's just preposterous. It's irrational having conversation with these people. Their standards are so uneven. Alright, so anyway, just thought I'd clear that up since I spent a whole couple of hours letting it just mooze through my head for a minute about this stupid locking thing. Not that complicated. The principles are already there. We already know, you know, how materials react in terms of this whole lens law, opposite field creation. And you just, if he had a little bit of imagination, he could have figured it out himself. But yeah, can't do any of that. Can't think outside any other box than what his professors of bullshit tell him. Anyway, enough. Until the next time and such.